So like, it seems like I could be optimized for the matrix healer. Because in a way, the person is like, they're just like checking every element and we compare it. So like if you could somehow do that on like maybe, you could promote similar algorithm. Or you do like 3M plus
Free ride for 30 years. While you write your programming software and we made it faster. Right, guys? That's over.
There's another programming with this. There's like 18.
Singapore.
I don't know if part of it, but oh, I think it's
You know, as part of the course preparation, I always try to select a song to play before the lecture that fulfills the agenda of the day that we are teaching. But yesterday, I'm kind of like running out of ideas. Then it comes to me that we are talking about memory hierarchy. So there is a feeling of like layers. So that's why I picked the song "If You Are Over Me," right? Because it sounds like someone is over the other one, so it's higher hierarchy. But to be honest, I didn't pick that song for that purpose. It's just like, okay, I like the vibe of the song, right? Sometimes you don't need a reason if it's not about science. But today we are talking about science, so you really need to know the reason why we have cache misses so that we can address their issue accordingly. So again, this is a big picture. I don't have to talk about again, but what right now you have to recognize that is the most critical issue in modern computer architecture. If you don't address it properly, then it's typically the memory issue. So if you look at the performance gap between processor and memory, it's 1,000 times difference. So given that every instruction comes from memory, every piece of data comes from memory, if you don't find a way to mitigate this gap, it doesn't matter how fast your processor speed is, it doesn't matter how good your processor is, how fancy your GPU is, if you don't get rid of the memory issue. So turns out that our modern solution is that we build memory hierarchy, and it's not just any SRAM, and we add multiple layers of SRAM. So it's hierarchy inside hierarchy, right? So L1 is over L2, L2 is over L3, and the processor only adds L1 for stuff, and L1 will automatically fetch and accommodate stuff in its location to give it to the processor. It's a very hierarchical structure, and you can think about in a company, typically you won't like have access to the VP, right? I'm exceptional because the VP is actually my instructor at UC San Diego. So, but anyway, but the thing is, that most of the time it's a hierarchical structure. So you don't report to your VP, you report to your manager. So you can think about like L1 is the VP, and processor is the CEO, right? And L2 is a layer below VP, and you're probably the memory, and L3 is probably your manager. So most of the time, processor only asks the L1 for data, and L1 will figure out how can I accommodate these pieces of work, these pieces of data in my space, and then as others provide the materials. So that's the memory hierarchy. However, accessing memory hierarchy has a lot of small steps that you have to know. And in a lot of cases, as a software engineer, we still need to know how cache works so that we can simulate the behavior of cache, so that we have a better idea regarding how this piece of code would perform on the given hardware. So it's really important that you know the parameters of your memory hierarchy so that you can simulate the code accordingly. So the formula that I would teach you here is C equal to ABS, where C is the capacity, B is the block size, S is the number of sets, and A is the weight associativity. And using the equation and the corollaries that I provide in this slide, you can actually get what are the tags, what are the set indexes, what are the block offsets, so that you can simulate the sequence of memory addresses that your code is going to access. And there are also another thing that's also important in figuring out the memory behavior is that why we have cache misses. And it turns out that there are 3 different causes of cache misses. One is the compulsory miss, typically the co-star miss. There is another capacity miss, meaning that your cache is simply too small to accommodate the working set within a given window of time. And conflict miss means that the access pattern, to be honest, the access pattern of your code is just not a good fit of your cache architecture in a way that even though my cache is not full, I still get cache misses. So if you recognize the cause of your cache misses, you can better know what to optimize. So one of the examples that we are giving here is that, okay, if I want to address conflict misses, on the hardware side, what can I do, right? So you can choose a processor with higher associativity. So it turns out, if you look at NVIDIA Tegra, right, most of the misses that we got, okay, I finally got this table for you. Yes, the last time I forgot to attach the cost of misses. But if you look at this table, it turns out that most of the misses that we are seeing in this 100% miss rate are conflict misses. So it turns out, if you really want to improve the performance according to MDOS, so if there's one thing we could do, then we have to eliminate those conflict misses. So turns out that the best way, the easiest way is that, okay, forget about NVIDIA, let's embrace Intel, right? So turns out, if you have an Intel processor with A-way associativity cache, you will avoid all those conflict misses and get performance a lot better in a way that it's only 12.5% of the cache miss rate and conflict misses are gone. So that's where we end in the last lecture. And today we are going to continue talking about the remedies of cache misses, and let's start with the hardware optimization and then the software optimization. So we have been talking about the hardware optimizations, and there are more hardware optimizations we can take. And sometimes you're thinking about, okay, I'm not Intel, I'm not going to build an A-way set associativity cache given the process technology that I have, the engineers I have. What can I do? How can I eliminate this 100% cache miss rate so my customers like Tesla won't complain? So turns out that it's really important to read this paper by Noam Jopi, improving direct map cache performance by the addition of a small fully associative cache and prefetch buffers. So Noam Jopi is, you will read 2 more about his papers in the rest of the quarter. I would say he is probably one of the most influential computer architects in industry. Why am I saying in industry? Because he is not teaching in any university, in any capacity. And he started his career at HP Lab, which is, no, actually Compaq. I don't know how many of you ever heard about that company, probably in some kind of computer history book. And then that company later acquired by HP, Hewlett Packard, so that's why he became part of the HP labs. And the story is that Intel used to have the tradition to collaborate with Compaq and then HP in developing their server processors. So turns out that Noam Jopi is in one of the teams that developed those server processors together with Intel and HP. But later on, as a lot of you know, HP is not that intensive player in server market anymore. It's transitioned to a company that's mainly focused on like health-related stuff, equipment-related stuff, or what you know the best, right? A printer company, right? Which have higher profit than any other thing that they have ever made. So turns out that Noam Jopi is now at Google. Intel is actually building the tensor processing unit, which you will later learn in this quarter. But from his profile, you can hear he is very influential in a lot of ways that he has been in pure hardware solution company and now shifted to companies like Google. So you know that computer architects, we are essential to the core of many companies. And right now the fact is that none of the hardware company can produce hardware or build systems that fulfill the demand of software companies. So it turns out the software company has to have a team doing that. And that's why you see John Hennessy, David Patterson, Noam Jopi, and a lot of computer architects, the best computer architects that I can come up in my mind. If you don't know where they are now, put Google first. And then probably Amazon. They are probably, or Facebook, they are probably in either one of the companies. And that's why when you see the recent thing about Intel, it's all kind of like negative. People are thinking about the future of Intel because all the hardware people, they are now working for a software company. So that's the most important, I would say, warning for traditional hardware companies. But it also tells you that, like, in the past you think, okay, if I'm a good programmer, I can be hired by Google. But right now, I can tell you, the trend is changing. If you are a good computer architect, you are more likely to be hired by this large companies. All right. So, but set it aside. I believe you have read Noam Jobi's paper. Did you? Okay. According to recall Noam Jobi's paper from your memory, can you answer this question? Looks like we have quite a few responses now, so let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looking at your initial votes, looks like, okay, C and D, they are popular answers, so why don't you guys discuss with each other and see what you guys get?
I don't remember but I know there's another besides just I don't remember if it was there was
Hello? Hello?
Right, yeah. Tuesday. I totally different.
Is What? Okay. Let me try again. How about now? Try now. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like they don't give me the battery, the backup battery for the microphone, so you can hear the original voice from my lovely buddy today. But I cannot guarantee the effect of recording today because the microphone is actually not working. Okay, so after discussion, this is what we got. Okay, so more of you think the answer is C, but still sufficient amount of you think it's D. So, let me see. So what do you guys think regarding the answer? Which one would be helpful? Which one would be not helpful? What's your name, by the way?
Gwen.
Gwen?
Yeah.
Okay.
I think that should be helpful just because the way that it's accessing remedies.
Okay, so how prefetch would be helpful?
I'm not sure specifically.
Okay, what's prefetch about?
Just like retrieving the data before your specific.
Okay, so it retrieves the data before, ahead of time. So it's helping, what kind of methods in your perspective? What's a rough idea? The name is?
The initial ones, I think.
Yeah. So, right? Because it fetch data ahead of time. So, if it's cold darkness or say composite method, right, then it helps. Okay, what else? What other do you think it will help? You select C, right? So there must be another one. Do you want to do this fun thing? Okay, so now some of you said prefetch. There is missing cache, victim cache, string buffer. Now I say 1, 2, 3. What's the other one in your mind that would be helpful? 1, 2, 3.
Victim cache.
Victim cache. Okay. What is victim cache? Why is it helpful? Finally coherent answer this time. What's your name?
Right.
Brian. Okay. Because I need some other friend than Aaron. Because one day, like my therapist told me that you need more friends. Okay, Ryan.
It's a small block of cache that's captured like in blocks. So and it swaps with the like the name register whenever there's a hit to victim cache.
Okay. So the idea of victim cache, a lot of you got it, right? So it's like a shelter of data being kicked out from the cache, right? So, but if we got a room for the cache again, or if someone really needs that piece of data again, we can put that data back, right? So that's the idea of victim cache. So you think it would help? So how about missing cache and string buffer? What do you guys think? Or you just don't remember who they are? Okay, that's okay, right? So looking at prefetching, so the idea of prefetching is this, right? Most of the time, the access pattern of your memory can be somewhat regular in a way that we know you have spatial locality. You have temporal locality, right? So there is locality in your code. So if we can figure out the locality from the hardware perspective or the software perspective, then we can potentially ask the cache to fetch the data before we actually need it, right? So for example, if for this piece of code, the spatial locality is really good, right? But typically what would happen is that when I access D0, you know it's a miss, right? So what would happen is that, okay, I ask L1
give me the data, but L1 say, I don't have it, right? So waiting for me. And it will take like a lot of time for the L2 access to come back. And then finally, we can start working on D0 and D1, right? And because then later on, the story you know, we have a block of data inside the cache. But what happened the next time when we access D8? Again, it's another mess. So we have to ask the cache to look for it and return it, right? So then we can resume our work on D8. And fortunately for D9, D10, and et cetera, right? Everything will be served. So every once in a while, you will suffer this long latency when you access cache. Are you satisfied with it? Or you can live with it? Are you going to live with it? If you are the CEO of a company, right? Every time when you ask your VP, hey, think about this. Microsoft has ChatGPT. Do we have something? And your VP is always telling you, okay, give me a month, right? Let me figure that out, right? Is that good enough? What's the next thing you are going to do? Fire the VP, right? So that's probably not going to work out. So our processor would definitely perform very well in a way that, okay, if I can prefetch the stuff. So for example, right, as a VP of the company, you keep investigating what other companies are doing, so you can guess what your CEO will potentially ask you to do. Like the day before other people announce ChatGPT, you already know that, okay, it looks like they are doing something together with OpenAI, so maybe ChatGPT is the next thing, right? So we should have something called BART in hand. So we can arrange a demo, which they bombed just a few days later than ChatGPT, but that was the story, right? So the thing is that you have that thing in hand, right? So prefetching is like that. So it's either the hardware or the software giving a hint, and the hardware or the software collects sufficient amount of information, and then judge if I should fetch the data ahead of time. So for example, saying that if the hardware recognizes that, okay, there is always a cache miss every 8 times of memory accesses. And then, surprisingly, every time when you have the memory access, the memory address is always 64 bytes away from the address that you are missing. So it's intuitive that the hardware can conclude every time when I see a miss, I should fetch the data that is 8 double elements away from the current element, right? So what will happen is that, okay, when I see bit D0 is missed, okay, this is compulsory miss. I don't even know that you are running this program, right? So it's a miss, but again, I know that, okay, there is a behavior that when there is a miss, I need to prefetch data that is 8 bytes, a block away, because I know very likely you are going to do that. So in addition to just the current miss, I issue a prefetch request that is fetching the next block, which I'm not currently using, but I can potentially use in the future. So what will happen is that when L1 serves the miss, right, again, this time is blocked. But whenever L1 has the free bandwidth, for example, when the CPU is doing other stuff, the L1 can access L2 to get the next block ready. So now, when I access D8 this time, because that block is already prefetched, so I don't have to wait. And in the meantime, your processor can continuously prefetch the upcoming block so that you can completely get rid of those misses, right? Okay, so that's the idea of prefetch. And in modern computer architecture, there are 2 common ways that prefetch would occur. The first way is the hardware prefetch. And in fact, both Intel and AMD, or recently I heard Apple processors, they have super smart prefetcher that would prefetch the data for you implicitly. So you don't have to explicitly issue those prefetch requests, and they will get the data ready for you. So it's kind of like problematic for this class in some sense. Sometimes you will see, hey, Professor, the miss rate that I measure from here, from the performance counter, is slightly different from the performance that I expect. But that's just because this modern processor, they do a lot of fancy stuff. So that's hardware prefetching. And the other thing is that as a programmer, right, you have a better idea of your program behavior than the processor, because what the processor can do is that they treat the whole software as a black box. And I can only see the memory address sequence that the software is accessing, but not the true software behavior. But as a software programmer, you know what your algorithm is going to look like. So you can insert prefetch instructions. And there are two types of prefetch instructions. So for those computer architecture doesn't have an explicit prefetch instruction, the easiest thing to do is that you can load your data into a 0 register. Like for example, if you have read a book in RISC-V, there is a register code X0, which no matter what you do, it's always 0, right? If you don't know that, it means that you just didn't read the book. And the second one is using prefetch instructions. So for example, in Intel architecture, there is an prefetch instruction in x86. And GCC can also has a flag fprefetch loop array, so that if it says it's a loop, right? Loop is something very standard, very easy to tell that there is a regular behavior. So these are the two ways that we can have prefetch instructions. So to show you how effective a prefetch instruction could be, or prefetch technique could be, let's show a demo now. Is something? Okay. So, okay, let's start with the demo here. Memory hierarchy. Okay. So, cache performance on real machines. So we have this, oops, this. Okay, so the last time we have the cache performance here. Okay, so right now let's try the prefetch. So for x86, we have the prefetch instruction that is allow the programmer to insert the prefetch. Now I have a pieces of a sample code here is matrix transpose. And this is a highly optimized matrix transpose code. So you are going to see a lot of vector operations here. And there are a lot of swapping here. And if you check the code, one thing I do is that I insert an prefetch instruction here that before I am doing the current block of data that I want to transpose, I would prefetch the next matrix tile that I'm going to transpose. So that's the idea of this pieces of code. So let's take a look, right? So first of all, I try to run this program on an Intel Core i7 processor, and without prefetch, the speed is 0.52 seconds. Now, let's try to run it with prefetching. 0.56. Okay, let's try a different machine. So this is a machine that you are using for your class. So this is an AMD Ryzen 5 55,000 processor. And for this one, if you don't have prefetch, it's 0.68. But if you have prefetch, it's only 0.58. So what does that tell you? What does that tell you? Does prefetch always give you speed up? No, right? And why is that? Why is that? So looking at this, right? Again, with prefetch, what are you going to do? Where are you going to store the data that you are prefetching from? Still in the same cache that you are running your code, right? So let's say I have a cache miss, and then I prefetch another block in the meantime, and then technically, right, because this miss, I got 2 blocks within my cache. And then what your cache is going to do to accommodate the other block? Kick something out, right? Okay, but there is no guarantee that something that you kick out wouldn't be something that you would need recently, right? So let's look at this. One example that I have in NVIDIA Tegra 1. So for NVIDIA Tegra X1, if I do prefetch, what would happen? So first of all, I know I want A0, but this is a miss, right? And then I have a very smart prefetcher, right? So I know, okay, very likely you are going to have A8 to A15 later. So I prefetch A8 to A15. Make sense? Makes a lot of sense, right? Now, I have B0. Again, I do prefetch. I have C0, I do prefetch. I have D0, I do prefetch. I have E0, I do prefetch. But at the time I prefetch E8 to EA15, what happened? Who am I going to kick out? No, A8 to A15, right? So it turns out when I access A1 again, well. So first of all, right? This miss we cannot replace. We cannot improve, right? But the thing is that, right? When you prefetch E8 to E15, it will kick out A8 to A15. What does that mean? It's still going to be a mess, even though we have prefetch, right? So does prefetch help? Does prefetch help? The answer is no. It's still 100% miss rate, even though you have prefetch, right? So sometimes we think prefetch would be helpful, but if you don't know what the underlying architecture, if you don't do this kind of simple cache simulation, you would issue prefetch requests on a processor that doesn't need prefetch, or prefetch doesn't even help. And there is a more complicated issue with the Intel processor, as I mentioned. So for the Intel processor, I just mentioned that they have the hardware prefetcher. So if I additionally issue software prefetching instructions, actually the software prefetching would compete with the hardware prefetching, and it will kind of like saturate your L2 bandwidth. It will also create more conflict in your L1 cache because you have to accommodate more prefetched blocks. And turns out it makes the performance worse. And fortunately or unfortunately, on AMD processors, their prefetcher is not that smart. So software prefetching is still helpful. So I would technically say if you try to issue software prefetching and if it works on the processor, or it means that the processor's prefetcher, hardware prefetcher is not that smart. So that's a very good way to test how smart your prefetcher is. But the conclusion here is that, well, if you don't have enough way associativity, for the example, on NVIDIA Tegra X1, or your hardware already have a prefetching technique, then software prefetching won't be helpful. Right? So this is a case where no matter it's hardware prefetching or software prefetching, it won't be helpful. Okay, so as a remedy, non-Jopi say, okay, let's do a string buffer, because the cost is simply because your cache doesn't have sufficient amount of way associativity to store those prefetched blocks, and turns out that it will kick out the data that are really essential, right? So for example, this prefetch is just a prediction. They shouldn't be given higher priority than the real data that you're working on. So a software company, for example, right? It sounds like I'm complaining a lot of things, but for example, we don't even know like ChatGPT or BART is the future. Should we let it blocking the most critical task of the company? Presumably, no, right? But that's not the reality. But anyway, okay. So here's the thing, right? So what non-Jopi proposed is that let's add another buffer for this kind of predicted data flow, which is string buffer. So the basic idea is that we build a small fully associativity cache. For example, 8 entries in total. So the search speed is still very fast. So when you need something, first of all, there won't be a conflict between those data prefetch, and second, we can still search it in a very fast speed. And then, let's combine this together with the prefetcher and see, and whenever I have a cache miss, I also look for the string buffer to see if the data that I need is also in the string buffer. So, that's the idea of string buffer. So in this way, when I have a cache miss, I still fetch the block as the usual. But for the prefetched data flow, it goes through the string buffer. And only when L1 has a miss on the data block that prefetch the string buffer has, the data will go into the main cache. So that's the idea of string buffer. So a similar idea to string buffer is called miss cache. So the basic idea of missing cache is that it's a small cache that captures the missing block. So prefetch is a small cache that captures string buffer is the small cache that captures the prefetching data. And missing cache is the small cache that captures the cache blocks that a cache miss needs. So whenever I have a cache miss, when I get the block, I not only have the block returned to the L1, but also have the block, another copy of the block in the miss cache. So what would happen is that, okay, if someone kicked my current block out, right, then I can still find the block that I previously missed in a miss cache. Right? So it's a shelter of data. It's a duplicated copy of the data that I missed. So if the original data got kicked out, I can find a copy here. So what kind of miss can it address? Conflict miss. Right? So what's the majority of misses that we have in the NVIDIA Tegra X1 processor? Conflict misses. Right? So do you think miss cache would help? Do you think miss cache would help?
Yes.
Yes, right? Because it's addressing the conflict misses. Right? And for the string buffer, it helps to reduce compulsory misses. is there any compulsory miss in NVIDIA Tegra X1 when running this matrix code? Yes, right? Although not majority, but it still helps, right? But with prefetch, simply with prefetching, it's not going to work. Okay, so when you look at the miscache, some of you, I can see your face, right? It's like struggle together. So you must find there is a problem of miscache. What is that? What's the main problem of miscache? What do you think, miscache? Think about miscache. Is it good? It's good in a way that it addresses conflict misses. But is it very efficient in terms of the space utilization? Yes or no? Ryan, do you have something to tell? Today you are my best friend. I have better an errand for today.
It captures the missing blocks. How do you give a definition of missing blocks again?
So whenever you have a cache miss, right, you not only return the missed block to L1 cache, but also have a duplicate copy of the same block in this cache.
Yeah,
That's a problem.
space.
Right, because you have a duplicated copy of the block. You have a duplicated copy of the block. I can use my hardware more efficiently, right? So that comes up with the idea of victim cache. So instead of create a duplicated block, whenever cache is missed, the idea of victim cache is that I only capture those cache blocks that are victims from a cache miss. So previously, you capture the cache block that a cache miss needs. Now, you capture the block that is kicked out. So what's the difference? If you capture a block that I currently miss, then you will create duplicated copy of blocks in both of them. However, if you just capture those blocks that get kicked out, either one of them is in victim cache or in L1. But you won't have duplicated copy of data. So you are actually effectively enlarge your cache size. You hear the difference? So this is a better way of doing it. So in the paper, right, Joby say that, well, for entry, victim cache can remove 20 to 95% of the conflicts of a 4 kilobyte direct map data cache. Isn't that effective? Right? Thinking about in your NVIDIA Tegra 1, the majority of cache misses are gone because of this small addition, right? So if you are a company and and this is the experimental result that they give, right? So if you're a company that you don't want to spend a lot of money building very luxury cache, then victim cache is your solution, right? So it turns out that if you look at what can help Tegra, right? Prefetch, it could be a good idea if we do it right. So for example, when I do prefetch, right? Well, I think for the NVIDIA Tegra example, it won't help anyway, right? Because they will get kicked out later. So, and most of the time, right? First of all, get prefetch right is difficult, right? As I just showed you, right? So, if you don't have additional hardware support, prefetching is like a hit or miss. Sometimes it works, sometimes it doesn't work. And for the NVIDIA Tegra example, it doesn't work because we just don't have sufficient amount of weight associativity to store this many concurrent blocks that we need to access. So it turns out you need an additional buffer to store your prefetch data, which come with the stream buffer, right? And the other one, which a lot of us identify, is the victim cache. And again, miscache is another way to improve conflict misses. So it turns out that 3 of them here are helpful. 3 of them are helpful, not 2 of them. Okay? Sounds good? Okay. So there are more hardware techniques that can improve memory performance. So first of all, by default, all the hardware operations are blocking operations. So the definition of blocking operations in software and hardware are not too different. In a way that when we say an operation is a blocking operation, it means that you have to wait the operation to return, to resume your execution. So function code, blocking or non-blocking. Is function code blocking or non-blocking? Are you guys computer science students? Blocking, right? Because you have to wait a function to return. So by default, the cache operation, the memory operations, or in general, all CPU instructions are blocking operations. In a way that when I fetch a block, I have to wait the block to return before I can issue the next operation. However, if you have a cache miss, and if your data is in the DRAM, you have to wait thousands of cycles to get it back. You don't want it, right? So turns out, this is what we do, right? So the reason why you have a blocking code is because you only have a single server to your request. If you only have a single server to your request, that's the reason why you have the blocking code. So if you really want to make something non-blocking, one of the ways is that you have to create multiple servers. So in hardware, it's very expensive to have duplicated controller to control on the same thing. So what we actually do is that we make your memory module or your cache module multi-partition. And one of the most common partition is called banking. So in DRAM, you can issue a request to one bank and then issue another request concurrently to another bank. And both banks, they can perform operations in parallel. And so in this way, it will be virtually non-blocking if their address are not conflicting in the same bank. So let's say, if I have a processor, and if I have a few memory requests, but fortunately, if they are belonging to different memory banks, in the baseline operation, we have to execute this memory request in serial. We have to execute this memory request in serial. However, if I have multiple banks, I can immediately request the next bank whenever I have done my job in issuing the current request. And then you can see the significant reduction in total latency of getting your data. So that's one common optimization that you will see. So that's why when you buy your hardware, sometimes you will see, well, multi-bank the DRAM, multi-channel the DRAM. They are all coming from this concept. So right now, this is the idea of multi-bank access. So I want you to think by how much we can speed up from the idea of multi-banking. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. All right. Looking at the answer, we definitely need some discussion. So why don't you go ahead, discuss with your friend for another 90 seconds.
So it's 9-0. Actually, are we doing? I guess it's roughly one round. Say on second, from second 0 to second 1, we assign now 10 seconds.
I did because I did first 4 plus 11. But that's what it is right now.
After that, another 8 seconds. And then 10.
Oh, you're right. I started at 1 hour. That also good.
So 43.
All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so looking at the answer, now more of you think it's C. So I have to say sorry to Aaron.
Okay.
Are we still friends? Okay. So what do you think?
I think that it's a 3 times speed up because originally it will take. If we assume that assigning the request takes 1 nanosecond, then it'll take 11 nanoseconds to process each request. So 4 times 11 is 44 nanoseconds. That's the baseline.
Okay.
If there's 4 banks for pipelining, then it takes 1 nanosecond to assign each one. The last one will take 4 nanoseconds plus 10 nanoseconds.
Okay. So here I actually assume issuing a request is no overhead. So simply regarding, but your calculation is makes a lot of sense though. Right? So in serial, if we serially execute this memory request, it will take 40 nanoseconds in total. But if we have it banked, right, it would take 13 nanoseconds. So it's effectively around 3 times. Right? It's not 4 times because they are not completely in parallel. However, good enough. Right? So that's why multi-bank cache is and pipeline access is one of the most popular. Yes.
So, is that possible? These requests are not independent?
What do you mean?
Like, one request is based on the others?
Okay, so you see if one request is not overlapping the others. Okay, Is it possible? So it depends on how good your memory allocator is designed in your C library.
Okay.
But you got the right point, right? Most of the time, are we this lucky? Maybe not, right? But it's the best practice we can do, given the hardware cost. Okay, sounds great. Okay, so another thing, right? We were thinking about, okay, we want to enlarge the block size so that we can eliminate the compulsory misses. However, we also learned that it's almost impossible to build like a 64-byte wide bus because they are very expensive, right? So if you look at the bandwidth between each unit, it's typically 64-bit because that's the most cost economic size of your cache. And remember, they are all your bandwidth because they are all wires. And you have to build very wide wires, but your area is more than you can imagine. So when we handle a mess in this case, right, what would happen is that if I have a cache block, typically what would happen is that when you have a mess, is that, well, if you are unfortunate that you find a victim block and it's a dirty block, then you have to write back the whole block, right? So given you have limited bandwidth, you have to do multiple writes. You have to issue multiple bus transactions to send your block to the lower level memory hierarchy. And then you can fetch your blocks back with multiple bus transactions, right? So that's the origin, that's what we have for now. But the problem here is that if I want to go through the whole process and restart, it just takes surprisingly long, right? So a trick that we can play is that, okay, we still have to write back first. However, if the word that we are requesting is already there. So for example, most of the time when you miss the very first item within a block, right? So as long as the word is arriving in the L1 cache, that's just let the processor go without waiting for others. So you can restart your work earlier. So that's the early start. That's the early start. So the idea is, if you have a really large cache block size, for example, 64 bytes is already 8 times larger than the current bus bandwidth, then we should apply the idea of early restart. Whenever your word is there, just go ahead and run it. And you can do even more fancier. So for example, what if your word is not in the very first block of the missing block? So you can also, if you have a smart enough memory controller, you can adjust the order of getting the words within a cache block by making the critical word first. So then it will allow the processor to resume the work earlier. So this is another trick that the hardware can play. And another thing that's also problematic here is that even I have early restart, I still have to wait for the write back, which can potentially trigger more cache misses, right? So what should I be doing? So the solution is, let's add a write buffer, right? See, if you ever if you ever read some of the operating system paper, you will also see that buffer is the solution to all the situation that you need faster response, right? So same thing for a computer architecture is that if I want to have a faster response, let's just add a buffer. Buffer is a great idea. It's if you check Buffalo Emerson's paper, I don't know if you read it in our phone system, but if you ever read that paper, right, he also said buffer is a great idea. Okay, so the idea of write buffer is that, okay, if I have a traffic of write back, let's just put the write traffic in the write buffer and then fetch the block. So it's kind of like similar to the string buffer or the victim buffer idea. Here I have a write buffer. Whenever I have a write traffic, I write to the buffer, and then after the data is presented in a buffer, I can already free up the cache location, and that location serves the reading data. And whenever your cache has a free bandwidth for the write, then we can present the write back data to the lower level memory hierarchy from the write buffer, but not occupying the bandwidth of your L1 cache. Right? So that's the idea of write buffer. So this is also a very highly optimized, very frequently seen optimization. Okay. So sometimes, right? We may have double count when we are writing data. Because now, not only, because we have locality, right? So sometimes your writes, you may have to write your data multiple times, not just once. You may update your data neighboring items multiple times. Right? And it seems like we have to perform this write operation so many times. So another thing that's called write merge is that since the application has locality, so write buffer delays the write to a lower level memory hierarchy. And whenever there is another write to the block that I currently have in the write buffer, I can present that write in the current write buffer, instead of getting it issuing multiple requests. So that's another benefit of having a write buffer, to avoid the double penalty of write. So now, you have learned a lot. If I want to ask you, who can help improve this rate? Can you give me an answer? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, I bet we need discussion, so why don't you go ahead and discuss with your friends.
So yesterday is like and now I'm like the time entry
Yeah.
Decided why he wants to get back on right. Well, I figure if it's gonna miss, it doesn't matter. You can go to the bank.
That is true. I think I was thinking right. The rule was about 3. That's the same as the ones that it's held after the party. But I was also thinking you could perform forward for
But obviously, this
well, that would also be part of the prefetching, which would help with the compulsory. Why?
Okay.
Nah, I think that you have to argue too hard for it to be right. Because I mean, theoretically, you pipeline such that they're arriving right as you have it because they take so much.
All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, okay, C is still the most popular answer. Anyone would like to share your discussion from your group? Okay. What's your name?
Ivan.
Ivan.
Well, we definitely agreed that prefetching counts since we talked about how it helps with the
Okay.
compulsory misses.
Okay.
But then we were divided on whether, number one, the non-blocking pipeline would help, because it would technically help with the prefetching, which would help with the compulsory. We could pipeline it such that you could fetch stuff right as it was needed.
Okay, but simply, this technique itself, is it addressing cache miss rate? No, right? You just make the response time of cache miss faster, but itself doesn't reduce the amount of cache misses. Do you agree? Okay. How about the second one? Ryan, do you have something to say?
Like everything here was besides prefetching are based on latency and bandwidth optimization.
Okay. So for write buffer, it's also help the write response faster, right? So if you look at everything here, the first one is try to address the miss penalty and insufficient bandwidth. And the second one is also address the miss penalty. And prefetching is addressing the compulsory miss, and write buffer is again the write miss penalty, right? So turns out you need to be clear about the definition of miss rate. Miss rate is about the number of misses. But for those other techniques that we listed here, they can only improve the latency of serving a cache miss. So they are more about cache miss penalty instead of the cache miss rate. So that's why only one of them is helping the cache misses. So here's a summary of the optimizations that we have been looking today. Prefetching, compulsory miss. Write buffer, the miss penalty. Bank, pipeline miss penalty. Critical word first and early restart, that's the miss penalty part. Okay, so looks like those hardware techniques typically doesn't help improving the miss rate, right? So it just alleviates the problem, but it doesn't address the problem. So now I'm going to tell you who can address the problem, right? It's actually you, the software programmer. So one of the things that you can do, right now you know there is a locality of data. So what can we do in the data layout to help addressing the issue? So here I present two data structures. So most of the time, if you are in object-oriented programming, people would like to just think stuff in a more object way, that thinking about what do you have, what are the characteristics, what are the properties that you have in your object. And let's create an object first, right? So for example, I want to create a big data table that tracks all scores of a student in UCR. So for example, the backend of e-learning system, right? So it turns out that I would have your student ID, I would have the amount of homework that you have, and then I will have your average GPA, for example, right? So the homework is an array, right? So that's why it's a pointer. So if I want to calculate the average, so saying that if I want to know if a homework is too difficult or not, I potentially will run these pieces of a code, which I go through each student's homework item and count the average of everyone's score in this homework item, and put the average in another array element, right? That's a typical code that you will write. Sounds very good. Sounds fulfilling the demand of your professor in object-oriented programming. And there is another version of the ugly code, which I create object of arrays, which I treat the student ID as a giant array in this big object. That's another way of using C++, right? And I have a homework as another two-dimensional array, which I store everyone's homework item as a row, right? And I also have average. So here is what it looks like. You will have an ID array, you have a homework array, and you have an average array. And if you want to count the student average of each homework, so it turns out what you will do is that, okay, for each homework array, I go through each student in this way and count their average. So my question for you, if you think about the behavior of the code that I'm actually doing is that I am doing this SQL query. Don't tell me you don't understand SQL query. Select average assignment 1 from table. If I want to do this, which of the following data structure would give me better performance? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. This is like a sudden death, right? A and B. Okay, looks like more B than A. So can people in B convince A in this 90 seconds?
My reason was for like a second one, you would index the segment array, and then it would all be yeah, just one check for you on the table. So if you're going to see an example, and previous through every record and find the average of each. So basically, there's like like 2/3, let's say, like under the abstraction that like because you have to select that, but it's just okay, but almost everyone or whatever. You only need 1/3 of that, so you have to like it's actually yeah. So in terms of locality, to get the averages.
All right, let's remember in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Ryan, what do you think? You think it's B, so you don't need someone to convince. But can you convince me?
Because I think query was a query to all the roles. So if you lay it out and sort of the like these where you all the objects are aligned in the rows, it will be easier to read.
Okay, easier to read. So it basically has better spatial locality, right? So if you look at the database table layout, right? The idea of B is basically so the idea of A, right? If you consider the whole student ID and homework as a big spreadsheet, right? Then the idea of A is basically a row store, which consecutive data will store the record for each student and consider each student as a row, right? And the structure of B is actually a column store, which I don't have the concept of which item belongs to which student. It's all consecutive columns, right? So that's called column store. So if you ever have the experience of taking a database class, presumably your teacher should tell you there is column store and there is a row store. And typically, most database systems, they are column store. Because if you check the workload that we have, right? What we typically would do is select columns rather than select a row, right? If that's what you want to do, you have to make sure that your data structure is aligned with your code behavior. So although object-oriented programming tell you that making every item, single item as an object is a good idea in terms of letting you guys understand what the program is doing. However, in performance, it's actually a disaster because it completely breaks the locality of code when you are performing workloads like database accesses. So that's another good example to tell you about. Sometimes you have to forget some of the principles of software engineering because software engineering is not designed for optimizing for performance, but optimizing for human readability and maintenance. So now, let me show you this quick example for these two pieces of code, which are exactly the same code that I have been showing you. And then this is similar to select assignment something from the table. And then let's run the demo to see what the performance looks like. So I have this two, and then I rerun these pieces of code with array of objects and object of arrays. So with array of objects, it would take 8 seconds to complete the whole workload. But for object of arrays, which looks uglier, would just take 0.2 seconds, which is 4 times faster than the other one, right? So sometimes, although the code looks ugly, however, it's faster, right? And that also tells you why. In a lot of cases, we thought the database should be like a spreadsheet and we store it according to the row order. However, most database systems are column store. Because of what? Because of this. column stores are indeed faster in workloads like select statements, which are most popular statement in SQL queries. All right, so in the next lecture, I will tell you more about the software optimizations, but before you leave the classroom, a few things that I want to remind you. First of all, we still have a reading quiz due next Tuesday, and the purpose of the next reading quiz is to make sure that you are familiar with x86 instruction set architecture, which you will use a lot in this class. And assignment 2 is already out, it's due next Thursday, and please start early, and some of you try to use STL outside of STL libraries in C++ the last time, but unfortunately there is no way I can make the Grayscope to support it. So when you use those libraries, I didn't say that you cannot use it completely, but make sure that you have tested on Grayscope before your submission. And to make sure that it works or not, you need to start early to give us sufficient amount of time and give yourself sufficient amount of time for the testing, right? And most of you care about the midterm. Midterm will be on May the 9th, not May the 4th, right? May 4th be with you. No, this is a factual. So it's on the May 9th, and I will give you a midterm, a set of sample midterm questions that you can practice. But we are post-pandemic, and there are lots of issues of online exam. So this time the midterm will be completely in person, and I don't allow any cheat sheet. And make sure that you are well prepared before you come to the midterm. Other than that, enjoy the rest of the week. I will see you next week.